So let's do a quick calculation. We'll do a pretty simple one and one that's relevant for the air around us. So assuming we're in a room temperature room at about 300 Kelvin, T equals 300 Kelvin, and most of the air around us is nitrogen. We could do this for oxygen too. They're going to be pretty similar. What is the value of URMS for nitrogen at 300 Kelvin? Let's go and calculate it. So again, we're just going to be using this equation, URMS is equal to the square root of 3RT over capital M, being the molar mass. All right, so M for nitrogen is 28 grams per mole. You can double check me, but that should be, it's 14 is the atomic weight for nitrogen, times 2 is 28. So if we want to express that in kilograms per mole, we need to divide by 1,000 grams per kilogram, which will give us 0.028 kilograms per mole. All right, so that's the value we're going to need. Now the other thing we need to do is put in R in the units that we just saw on the previous slide. Kilogram times meter squared over second squared over mole times Kelvin times 300 Kelvin. So our Kelvin are going to cancel. And then divided by our 0.028 kilograms per mole. Now we use these units again so that these kilograms will cancel here. Our moles will also cancel. And so we're going to be left with, thinking of just the units, the square root of meter squared over second squared, which is meters per second, which is a nice speed, right? A good speed unit, a distance over a time. So we have everything correct here. Let's go ahead and plug this into the calculator. All right, so we need square root of 3 times 8.3145 times 300 divided by 0.028, which gives us a value of 517 meters per second. That's pretty fast. So this is these molecules are zipping around at a good speed. So we're used to think about miles per hour, but this is a whole meters per second. So a meter is something like right. So it's 100 centimeters or 1,000 millimeters. Or it's about a yard or 3 feet. And so that's 500 of those in a second is how fast a gas particle is moving. Now, it doesn't actually get to go in a straight line. It doesn't get to go 500 meters before it runs into something else. Right? There's a lot of gas particles. So it goes that fast on average, but it's bumping into a bunch of things in between. So it doesn't like go in a straight line doing this. It has a random moving around in the air. But this is an example of how we can use this equation. And this value is going to change, right? If we change temperature or if we change molar mass, we're going to see that this value changes. So that's a quick example of how we can use this equation and how you would actually use the value of R and making sure to convert to kilograms per mole to be able to calculate a root mean square speed.